Hello everyone, my name's Josh. If you don't know me, I was a computer science examiner, so it kind of gives me a little bit of an insight into how marks are going to be given and how you can get those marks on there. I run a tutoring business and I was a teacher, head of computer science as well. And this is for the AQA Computer Science Past Paper 2023, Paper 1. I can't include all of the information on here just because AQA haven't released everything to do with it, so I'll try and do as much as I can, which will give you hopefully a little bit of help in these. And I'll try my best to essentially go through and explain some of these concepts as we're going along so that you're learning, not just copying down keywords from time to time. As I said, I'll try and do my best. So the first question that we've got is describe the process that should be followed to add an item to a circular queue. Okay, and I've included a little bit of information down here about this, so hopefully this will make sense. The main way that the main difference that we've got with a circular queue is it's essentially, with a static queue, it's going to go in a linear fashion. So it goes like 0 is the first item, and then 1, 2, 3, 4. Okay. Now, the problem with a circular queue, which is trying to overcome, is if we need to start re-entering data into the queue, it kind of works like a circle, like this. So that, as you can see here, 2 is actually the front of the queue, and then we've got the back of the queue, which is 0. So how does what this question is asking is, how does it know to put the value at position 1? And we need to write the steps of doing that. So I've included a little table up here. So these are where the marks are going to be given. Let me make that a bit bigger. So the points that I'd be going for on this one is going to be, so for mark number 1, we need to be saying we're always going to check. First thing that we're going to do is we're going to check if the array is full. Then what we're going to do is we need to get the current index, and then add 1 onto this value to calculate where the next available space is. And that's just called like the next pointer, okay? This is kind of 3 and 4. I'll put 3/4, okay. Now this is how it calculates a different value to it. What you do is you get the current index, so +1, which is going to be the next pointer. And then what we do is we're going to mod the next value with the max size of the list. All right. In this case, remember arrays and lists are different, and it has referred to as talking about arrays here. So that's a little thing as well. Lists and arrays are different, so do make sure that you specify the difference between the two of them, and then you place value at this point. So that's how it can calculate, even though that we're on, let's say 2, how we can get a new value of 3, and how if we were at 4, we can actually get a new, the next value is going to be at 0. Okay, so that's how it's going to go, and that's the five marks that you can get for going through that process. Okay, so for the next questions, there was a logic question, but I think the picture was some of the information of how to actually work it out. So if anyone can get me that'd be great, because then I can actually go through that question, but I can't do it because the question didn't make sense without the picture, and AQA haven't released it. So it says we've got a tree data structure, and it says state 2 characteristics that make a tree, and it's a 2-mark question, so I'm just going to write that over here. So a tree has a root, so it's going to have a root node up at the top, and each node has 2 values or no more than 2 nodes coming off it. So it means in a binary tree, it can either have a value that's less than it and greater than it, but it can't have, and it could have none, but it could have none, 1, or 2. For the next question, what it's asking us to do here is we've got figure 3, shows a subroutine that implements a binary search algorithm. Just a little thing as well, if you're finding this useful, we do have a group lessons, which you can find out more information about on my website, and we go through all of this kind of stuff all the time, and you can make suggestions and everything, and it helps to support the channel. So I'll put a link in the description about that. Okay, for this question then, what we're going to do is we're just going through the binary tree search algorithm. And how we do this is we're going to go through the nodes and search for it. K is the search value. So what it's going to do is it's going to be checking with the first value, so 0, if that is the value it's looking for. And what it's going to do is it's going to go while current is less than, greater than -1, because -1 signifies that we have come to the end of the binary tree. What we're going to do is if the tree data that we're at is equal to what we're searching for, that means we've found it. So then that's going to be true. Else, that what we're doing is we're still looking for it. So we're going to do if the data we're at is less than K, so the thing that we're looking for, K is greater than what we're at currently. So that would signify to us we need to go to the right of it, because the way the binary search tree works is it's going to go to the right of it if it's greater, less than to the other way. So current is going to equals tree, square brackets, current, and then it's going to be dot right. The next line is just going to be for the other situation, which is if it's less than it. So the value, so we're going to go to the left. And then finally, it's going to do at the end, which is just going to return false if the value is not there. Okay, so if the value isn't there, essentially what that's going to do is then we need to return false to let the person know that they haven't, is not in the binary tree. Okay, for the next page, we've got 3.3, which is there are similarities in how a binary tree search and a binary search algorithms work. State the big O time complexity for a binary search algorithm. Binary search, okay, not to get muddled up with binary tree search. So binary search is you've got a list of ordered numbers and you're going for the middle value each time. The way it calculates that is it does the position of the lowest value and the position of the highest value added together, divided by 2 to calculate the middle value, which then it checks that value to see, is that item the item you're looking for? And essentially, and then it goes no, and then it asks the question, if it's no, and then it will then remove half of the list that it knows the item is not on. Because if you're at 10, because it's an ordered list, and let's say the item you're looking for is 15, you know that it can't be less than 10 because it's an ordered list. And it's a way that you can very quickly find a value in a huge list. For 1 million items, I think it takes about 21 searches. So this one here is where it's asking us for what the big O time complexity. Linking this to big O time complexity now this is all to do with how long something, a big O notation is a way of showing how long something is going to take by putting a value to it, okay? And essentially there are, sorry to give it another plug, but in the group lessons, what we do is we go through all of the different, algorithms, and one of those ones in there, but there you go. Okay, so this one here is going to be O, so that's where it always starts at. And then the idea with this one is the list halves, okay? So the problem gets smaller and smaller and smaller, open brackets, and then this is the value which we're going to put in there. So it's going to be O log 2n, which essentially means like the number of values. It's that 2, I can't do it on here, but it should be like little. It's just essentially getting across the point that it's going to half each time, okay? And it says, explain why the binary search algorithm has a time complexity stated in the answer for this one. So essentially, the list halves itself. Halves itself each time. I'll put that over there. So that's why. So the way that the algorithm works is it progressively makes the list smaller, which is why it's a really, really efficient one. So I'm just moving it over just to make sure that it's all a bit clearer. As you can see, it's a bit of a work in progress, this, but we'll go with it. Explain why searching for an algorithm in a tree or a list is a tractable problem. Tractable is all to do with if the buzzword that I'm looking for in an examiner is that whether you can use the word polynomial correctly. So it means that it has a time complexity, how complicated it is to search, of O(n) squared or O(n) cubed. O log n as well, O log 2n, sorry. So yeah, it's those ones where it's not going to be a crazy huge number, okay? Intractable problems are ones which are exponential. So the difference with exponential big O notation is O2 to the power n. So that can very quickly become a huge number. Factorial in there as well. So it's those ones that you're looking for, which can very, very quickly get huge, massive numbers. So those are the kind of words that I'm going to be looking for. So for linking this one, so it's going to be the time complexity. Is not polynomial. Is polynomial. E.g., and then you may want to do like an O(n) power to the power 2, something like that. Okay, so that's going to give you that. It explains. It says heuristics can be used to work when working with an intractable problem, so one that it has an exponential big O notation, so it's going to be very, very difficult to solve. It has a solution, but it's just going to take a very long time to solve. So it might take a CPU, a million years to solve. So that would be an intractable problem. Explain what heuristics are. Heuristics are a best guess. Okay, so heuristics are a best guess which will take some information prior to carrying out the action, and it will try to reduce some of the searches or whatever action it's taking. So how A star, I know this is not on the AQA example, but it's a good example, is like instead of Dijkstra's, which checks every possible scenario, A star, what it does is it will have this thing called a heuristic, which will give the search algorithm some idea of what might be the best possible solution to take. So it rules out a lot of the searches, which saves the processor a lot of time, so that then it means that we can make decisions that may not be completely optimal. So doesn't always make optimal decisions, but makes it more tractable. So if you've got a very large problem, then that's something that you can do to work that out. So the next one there, which it says about explain what is meant by constant time complexity. So it means like as the problem, like the amount of stuff in the problem increases, the time it takes to do it stays the same. So more stuff, but stays the same, whether it's got 2 items in it or a million items in it. And I was looking around at different examples just to give you one. And the one that I got was hash tables. So that's, anyway, it's 2 marks. So what we're going to say is as the size of the problem increases, or size of the search, something along those lines, increases, the time taken to do it stays the same. So it's like it's constant. That's what it's getting at. Okay, people. So let's go for this question then, where you've got so we've got to do a bit of BNF, we've got regular expressions, we've got syntax diagrams, we've got all sorts here. I've included a little example of some BNF stuff down at the bottom there just to go through it. And essentially what you've got to do is look at these different languages which they've created, where you've got syntax diagrams, as I said, regular expressions, BNF, and you've got to work out whether something is legitimate, like is it a legitimate language, okay? So with A here, this here is generally something that you shouldn't see. So language A is not, okay? If we look at the example down here, which I got, which was just about making variable names, I think it was just putting that in there. So you set your values up, so you've got your digits, you've got upper, lower. And what it's got here is, it essentially allows it to stop. You've got your char, which is obviously going to use lower is a combination of lower, upper, digit, under, so underscore. And then what you've got is it then can either be char, and then it recursively calls itself. And that the format up there is just not one that is not one that is going to work. B's fine. That's just a normal regular expression, so that's going to be good. I thought this one here, if I'm completely honest, I didn't think this was a correct one. Okay, and I'm going to put that to you guys. It says in the mark scheme that it is the answer, but I just thought this expression here, you couldn't do that in there. So I would have actually marked that one as not, but you know, I'm always learning as well, as you can see. So it's just you know, maybe message or put a little comment in there and tell me what you think about that one. This one here, absolutely fine. So that one there is D is Y. E is on that one there is absolutely fine as well. It's just a normal syntax diagram. And this one here, also going to be a normal syntax diagram. Two things that I'm going to just quickly go through today is we've got, so it says, show that the language defined by the union, so we're combining these two together. So you've got this expression Bn or n is greater than 0. So that essentially means we're always going to have one of B, yeah, so one of B, at least, or more. And then it's just like or A or AB. Okay, so we just need to make an expression which combines those two together and gives us a situation of what could happen. So that's A, pipe, which is or, AB, or, now B, and then plus. Okay, so the plus means that you're always going to at least get one of it. Star means that you can have 0 or more. So that's the difference between the two of them there. So it's A or AB or B plus, so you can have as many of those as possible. And it says, explain what the meant by the cardinality of the set, the amount of values that are in the set.